Afternoon, sir.
Good afternoon.
Good afternoon, sir.
Good afternoon.
Oh Magu, Turulab.
Okay, so can you see the virtual blackboard?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So in the last class, we were discussing, we have started discussing the application of PN junction diode, and we were discussing series and parallel. We have discussed load line, and after that we were discussing series and parallel combination. And this was the thing. This was the last thing that we have discussed. That is parallel combination of two diodes, D1 and D2, where D1 and D2 both are silicon diode, and if this E external voltage is less than VK1, that is the knee voltage, D1 and D2 will be off. This will be the equivalent circuit, and if E is greater than Vk, this is the condition is less than equal to, if E is greater than Vk, so D1 and D2 will be in on condition, and this will be the equivalent circuit to similar voltage sources in parallel. This is valid. You can connect similar voltage sources in parallel, but there is no sense of doing that. Okay, no matter you connect infinite voltage sources, but there is no sense of doing that. I will be E of Vk divided by R. If you apply Ohm's law, at this terminal you have E, at this point you have Vk. So simple, the voltage difference E minus Vk by R. And this I will be divided, here you will have current I, and it will see two similar branches, so it will be divided into equal halves, so I by 2 here and I by 2 here. Okay, if you have three branches, so it will divide into three branches, three parts, n branches, so it will divide it into n equal parts like this. So you can see that having similar voltage sources in parallel is not making any sense. It is not causing any advantage. Okay, so voltage sources are always in series. If voltage sources are in series, then we can add or subtract according to their polarity, and current sources are in parallel. When current sources are in parallel, then we add or subtract their value accordingly. Okay, so for this voltage sources, we apply KVL. For current source in parallel, we can apply KCL. So now, in this case, I have taken two similar diodes. Both were silicon diode. Now, what if one diode is silicon, one diode is germanium? Okay, so now I'm considering this case. So one of my diode, this is external resistance, external voltage source E with external resistance R, and now I am having two diodes, diode D1 . Okay. Yes, Rahul. Unmute yourself. Rahul, do you want to say something? Okay. पता नहीं क्यों raise किया hand. So 1 minute. So if you have two diodes, diode D1, let assume it silicon diode, and second diode is diode D2, and you can assume it germanium diode. Diode D2 is a germanium diode and diode D1 is a silicon diode. So now VK values of their turn on values, VK values, knee voltage values are different. So VK SI is 0.7 volt and VK GE is 0.3 volt. Okay, and one more thing I am doing here. Okay, I am connecting this E to this R via switch. So this is a kind of switch. This is a kind of a switch which I can open or close as per my wish. So initially it is open. Initially the switch is open, and let us assume that E is greater than VK1. Okay, if E is greater than VK1, VKSI, by default it is obviously greater than germanium. So E is greater than VKSI, and initially when the switch is open, both the diode will be in off condition, so no current will flow because switch itself is open. Okay. So now when switch is closed, so I have now closed the switch. Now what will happen? This E is connected to this network. This E is connected to this resistance, and this resistance is connected to diode D1 and D2. So now what should happen? Anyone? Okay, it is a very basic concept. Okay, कोशिश करो, कोई कोशिश कर सकता है बताने की क्या होगा यहाँ पे? Okay. Yes, Rishabh.
सर क्या कहते हैं पैरेलल में तो पोटेंशियल इक्वल हो जाएगा, जो रेजिस्टेंस है वो उसमें क्या कहते हैं मतलब नेगेटिव पोटेंशियल की तरह मतलब वो हो जाएगा, माइनस IR हो जाएगा अगर वो लगाओ किरचॉफ लॉ।
ओके, एक मिनट यार, सिक्योरिटी म्यूट, अलाउ पार्टिसिपेंट। ओके ठीक है। नहीं, आपने ठीक तो नहीं बताया, नेगेटिव नहीं होगा। ओके, नेक्स्ट इज आयुष गोयल। यस आयुष।
सर
हाँ जी,
जो पैरेलल है तो वोल्टेज तो सेम ही जाएगी दोनों को,
ओके।
सिलिकॉन और जर्मेनियम को, तो लाइक रहने दो सर, नहीं।
ओके, अंशित एंड गुरकीरत। ठीक है अंशित। यस अंशित।
सर करंट जर्मेनियम से जाएगा।
अच्छा, ऐसा क्यों होगा?
सर क्योंकि जर्मेनियम की जो बैरियर वोल्टेज है 0.3 वोल्ट है, तो वो पहले ट्रिगर आउट कर जाएगा, और उस जर्मेनियम की ज्यादा है तो करंट चाहेगा कि जहाँ पे रेजिस्टेंस मुझे रेजिस्टेंस कम मिल रही है वहां से जाऊं, जहाँ पे रेजिस्टेंस ज्यादा मिल रही है वहां पे क्यों जाऊंगा।
हाँ एग्जैक्टली करेक्ट। एंड गुरकीरत, लास्ट कमेंट गुरकीरत से ले लेते हैं।
सर यही कहना था सर।
Okay. So yes, Anshit and Gurkirat, you are absolutely right. At the moment when you will close the switch, what will happen? First diode D2, which is germanium diode, D2 will be in on state first because its turn on voltage is less, comparatively less, 0.3. So GE, it will on first. Okay, so that will be the case. This resistance R, you have diode, silicon diode D1, and now your germanium is on, so plus minus 0.3 volt. E, voltage E. Let us assume some value of E. So let's take E equal to plus minus 5 volt. Okay, 5 volt is sufficient. So 5 volt, and this will be the case. Obviously 0.3, this will be in on state first. Now what will happen? This is point A, this is point B. So VAB is now fixed. Yes, I am coming to you. Let me complete first. VAB is 0.3 volt. It is fixed. Okay, so current I will flow here, and the moment it is in on state at point A, we have 0.3 volt, and now it is fixed. Okay, current now had a part. It will flow like come through this resistance, and it will flow across this. It will flow across this germanium diode. So because of this 0.3 voltage source, the voltage at point A will never cross this value 0.7. It will remain fixed at 0.3. So VA will be always at 0.3 volt. Okay, and the value of I can be calculated as 5 minus 0.3 divided by, let's say it is of 1 kilo ohm. So 1 kilo ohm. So it is 4.7 milliampere. So D2 germanium will on first, and VA is 0.3. So D1 will be off because of the same reason, because at VA the voltage is fixed now 0.3 volt, and we need 0.7. Okay, अब देखते हैं कौन है ऋषभ. ये आपका पुराना है क्या, ऋषभ एंड गुरकीरत? अगर हो गया हो तो हाथ, यू कैन रेज डाउन योर हैंड. ओके, साहिल एंड मयंक. ओके, यस साहिल.
सर आपको कभी टुरु लबू है?
कौन है भाई ये, हद है यार. ओके, यस मयंक. ऐसे करोगे तो फिर मैं डाउट लेने में कंप्लेन कर दूंगा डीन से, डाउट लेना भी बंद कर दूंगा. क्या कर सकते हैं अभी?
सर मेरे को ये तो समझ में आ गया कि आपने कैसे किया 0.3, पर सर सिलिकॉन से मतलब आपने उसकी 0.7 को नेग्लेक्ट कैसे कर दिया, समझ नहीं आया.
नेग्लेक्ट नहीं किया. जैसे ये 0.3 हुआ तो पॉइंट ए पे फिक्स हो गया 0.3. नेग्लेक्ट नहीं किया, 0.3 हो गया तो D2 ये पॉइंट ए पे वोल्टेज ये पहले ही 0.3 अपने अक्रॉस ड्रॉप करवा लेगा. तो ये ए पे फिक्स हो गया. ठीक है, अब ये दिस इज रूल दैट बिटवीन पॉइंट ए एंड बी वी कैन नॉट हैव मल्टीपल वोल्टेजेस. मल्टीपल वोल्टेज सोर्स हम नहीं रख सकते. पॉइंट ए और बी के बीच में एक ही होगा. VA माइनस VB एक ही तो वैल्यू होगी.
यस सर.
VA माइनस VB कैन बी जस्ट वन सिंगल वैल्यू. ऐसा नहीं है कि 10 वोल्टेज सोर्सेस आपने लगा दिए. तो तभी मैंने आपको याद होगा यहाँ पे मैंने ये स्लाइड यहाँ पे शायद डिलीट हो गई है. अदरवाइज तो मैंने स्टार्ट करने से पहले एक बार आपको कहा था. हाँ, ये है. ये मैंने लास्ट टाइम हमारी 10-15 में डिस्कशन हुई थी कि 9 वोल्ट इधर लगा दिया 6-3. तो ये इनवैलिड है. ए और बी के बीच में एक ही वैलिड सोर्स होगा. ठीक है, तो क्या होगा, ये 0.3 जैसे आया तो D2 कभी ऑन होगा ही नहीं. तो D1 सिलिकॉन है, कभी ऑन होगा ही नहीं. तो आप उसको डिलीट कर दीजिए उसको.
सर अगर बाय चांस मल्टीपल वोल्टेज सोर्स लगे हो पैरेलल में तो हम कौन सा लेंगे?
वैसे तो वैलिड नहीं होता. दैट विल बी एन इनवैलिड सर्किट. और इस केस में जैसे ये डायोड है, ये 0.3 का ड्रॉप करवाएगा, 0.7 का करवाएगा, तो मिनिमम ऑब्वियसली फर्स्ट इट विल 0.3 ड्रॉप पहले होगा. ये पहले ऑन स्टेट में जाएगा और उसके बाद ए और बी के बीच में 0.3 फिक्स हो गया. तो ये कभी ऑन स्टेट में आएगा ही नहीं. तो ये हमेशा,
हाँ मैं समझ गया. यस सर
है ना. सो मल्टीपल
Yes, sir.
वोल्टेज, दैट्स व्हाई आई हैव
Thank you,
लास्ट. This is not valid. Never ever. हाँ, if there is resistance then it is valid. अगर यहाँ पे रेजिस्टेंस होता, यहाँ पे ऐसा रेजिस्टेंस होता, तब ये शायद ऑन स्टेट में जा सकता था. ठीक है, तब कुछ यहाँ पे करंट फ्लो होता, वोल्ट तब जा सकता था. बट स्टिल वोल्टेज बिटवीन पॉइंट ए एंड बी विल बी 0.3. यही होता.
वोल्टेज वही रहता है, करंट हो सकता जाता.
करंट बिल्कुल जाता. बिल्कुल आप KVL लगाइए इस लूप में और ये ऑन भी हो जाता. जैसा कि लास्ट टाइम किसी स्टूडेंट ने कहा था कि अगर हाँ रेजिस्टेंस with some voltage source, तो हम उसको equivalent कर सकते, तो वो हाँ उसका सही summation था. If resistance is there, then you can have some, then there will be different currents I1, I2, I3, but still voltage between point A and B will be fixed, one single value. VAB एक ही चीज हो सकती है, VA minus VB, different तो हो नहीं सकती.
यस सर यस.
ये बहुत बेसिक फंड है, इसको क्लियर करना. अब कौन है? और आयुष गोयल. यस आयुष.
सर जैसे जो सिलिकॉन डायोड और जर्मेनियम डायोड है वो कनेक्टेड तो ए और बी दोनों, लाइक दोनों ए और बी से कनेक्टेड है.
इनिशियली तो डायोड है, दोनों ऑफ स्टेट में है ना.
हाँ तो सर वोल्टेज तो फिर दोनों को ही मिल रही है ना, एक्सटर्नल वोल्टेज.
इसको पॉइंट, इसके सिलिकॉन इसके अक्रॉस 0.3 ड्रॉप हो तो रहा है, इसके अक्रॉस भी 0.3 ड्रॉप हो रहा है, बट 0.3 इज नॉट सफिशिएंट टू टर्न दिस डायोड ऑन. ऐसा नहीं है कि डिलीट हो गया, फिजिकली तो लगा ही हुआ है ये. आप फिजिकल
सर 0.7 क्यों नहीं होएगा मतलब, लाइक
ये 0.3 ये पहले हो जाएगा ना ऑन,
क्योंकि उसकी लाइक कम है.
हाँ ये कम है, बिल्कुल ये कम है, तो ये पहले ऑन हो जाएगा ना, तो ये इसको ऑन ही नहीं होने देगा. ये लगा तो रहेगा आपके सर. हाँ फिक्स, दैट इज फिक्स.
ओके सर.
ओके, नेक्स्ट वी हैव प्रद्युमन. यस
सर आपने बोला कि 0.3 वाला पहले टर्न ऑन होगा. तो इसका मतलब जब हम स्विच को क्लोज करते हैं, जो ई है, पोटेंशियल डिफरेंस है, वो 0 से लेके 5 तक ग्रेजुअली इंक्रीज होता है कि डायरेक्टली 0 से 5 जाता है?
डायरेक्टली ओके. अगर हम उसको ऑन पेपर बनाएंगे तो ऐसे बनाएंगे, जैसे मैंने स्विच क्लोज किया इंस्टेंटली 0 था, वो डायरेक्ट, ठीक है, बट स्टिल दिस इज ऑन पेपर वी ड्रॉ, बट स्टिल नैनो सेकेंड माइक्रो सेकेंड कुछ तो होगा. वो दिस इज अ रियल प्रोसेस, एंड रियल प्रोसेस ऐसा हो ही नहीं सकता कोई रियल प्रोसेस 0 सेकंड में कंप्लीट हो जाए. तो वो भला ही 10⁻⁻18 सेकंड लेगा, बट स्टिल
मतलब ये इंस्टेंटेनियस नहीं होगा, बस काफी कम टाइम.
राइस टाइम फॉल टाइम वर्ड पढ़ा है ना आपका, पढ़ा हुआ है ये वर्ड, राइस टाइम फॉल टाइम. एक्चुअली जैसे आपका वेव है कैपेसिटर में, अगर आपको शायद थोड़ा सा दिमाग स्ट्रेस डालो दिमाग में, याद आ जाएगा. तो ये है स्क्वायर वेव, और अगर आप कैपेसिटर के अक्रॉस दोगे तो कुछ ऐसा आता है. दिस इज चार्जिंग, दिस इज राइस टाइम, चार्ज हो रहा है, दिस इज फॉल टाइम. तो इसका राइस टाइम बहुत 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 मतलब इसका तो राइस टाइम बहुत ज्यादा है, इसका राइस टाइम बहुत कम होगा. तो ऑन पेपर whenever we draw it on paper, it will look like that it is instantly rising, but no, it is taking some time. Even it is of order of 10⁻⁻18, 10⁻⁻32.
ये टाइम मतलब लाइट की स्पीड के अकॉर्डिंग होगा कि कोई और होगा?
नहीं, लाइट की स्पीड के अकॉर्डिंग तो नहीं होगा. इलेक्ट्रॉन का क्या है, जो भी ट्रेवल ऑफ इलेक्ट्रॉन वो समझ लो आप. बट स्टिल वी कैन नॉट कैलकुलेट इट, हमारे लिए वो कैलकुलेट हम नहीं कर सकते उसे कैलकुलेट. ठीक है, बट स्टिल दीज आर डिवाइसेस, दे कैन फील दिस. ओके, ठीक है. तो okay, so please do remember, these are again I am repeating, these are very very simple and very basic concepts. Okay, so please इसमें confuse नहीं होना है. Okay, next. Now I have taken two diodes in parallel. Okay, and both are connected. This diode D1 is connected between point A and V0. Diode B is connected between this point B. D2 is connected between point B and again the same point V0. So just 2 points are different. A and B are 2 input points. This is a junction point and it is connected to resistance. Okay, so now 4 different cases are taken. VA, VB. A is 10 volt, B is 10 volt. Second case, A is 0, B is 0 volt. And third case, A is 10, B is 0. Fourth case, A is 0, B is 10. This 10, 0, 0, 10, this is the meaning of this is that the magnitude of voltage applied at this point. This A equal to 10 means 10 volt voltage DC voltage is applied at point A. B equal to 10 means 10 volt is also applied at point B. Okay, so you have two different points, point A and B. So 2 factorial, you can have 4 different combination. Okay, so these are all the 4 possible combinations. So now we have moved to digital circuit. Okay, so the value of A can be either 10 volt or 0 volt, and similar for B, its value can be 10 volt or 0 volt. Okay, so I am defining here, let logic 1 is equal to 10 volt or 9.3 volts. So if the voltage is in this range, 10 volt to 9.3, okay, higher side, so I will say that logic is 1. And for logic 0, it is absolute 0. Okay, so this is how we define voltage levels in digital circuit. Either 1 means on, 0 means off, on and off. So in digital we have binary. Binary means 2, bi means 2, 2 means either 1 or 0. Okay, so this 1 and 0, what are these? These are basically this voltage levels. In electronics we have voltage levels. So meaning to say one is that output or input is logic 1. So I am saying that higher voltages are applied. I am obtaining higher voltages, and meaning to say that logic 0. So 0 volt, voltage close to 0 volt. Okay, so I can apply 4 different combinations. 0 1 1 0 1 sorry 1 1 0 0 1 0 0 1. Okay, now corresponding circuit for all the combination. For first, this will be the equivalent circuit. For second, this will be the equivalent circuit. For third, this will be the equivalent circuit. And fourth, for fourth combination of input, this will be the equivalent circuit. So let's discuss the first combination where A is 10 volt and B is 10 volt. So 10 volt is applied at terminal A. 10 volt is again applied at terminal B. Okay, and this 10 volt will be sufficient to drive diode D1 in on state. So 0.7 voltage drop will be there, and again at this point at point B we have 10 volt. So again this is sufficient to drive D2 in forward bias condition. So again replacing D2 with equivalent voltage source, that is 0.7. Okay, now what you have to do, you have to measure V0. You have to tell what will be the value of V0, and you can also measure current, there is no problem. Okay, so now this point is bifurcated into 2 different branches, this and this, and both are similar. You can see that 10 volt followed by 0.7, and in second branch it is also 10 volt followed by 0.7. So either you calculate voltage in this branch, equivalent voltage in this branch, or in this branch. Okay, the values will be same. दोनों का करके ऐड नहीं करना है, एक ही जगह पे एक ही पॉइंट पे कैलकुलेट करना है. Okay, so now I am taking this. Let's take this lower one B1. So now applying KVL into this loop. 10 volt ऐसे लिखा है, मतलब इस तरह से दिया होगा ग्राउंड से, इस तरह से इसको भी ग्राउंड से दिया होगा, इस तरह से नॉमेनक्लेचर खाली 10 लिखा है. तो it is understood that this positive is connected to this point B, negative is connected to ground. So now you can apply KVL across this loop. So the value will be 10 minus 0.7, and this is V0. So V0 is measured between this point and ground. So I can write directly V0, and by default V0 will be also equal to VR, because VR is also I into this 1 kilo ohm. Okay, so if you solve this, the value of V0 is 9.3 volt. So output will be 9.3 volt in this case, and you can also measure current. You can measure current I, that will be V0 by R, 9.3 milliampere. Okay, so here 9.3 milliampere is coming. If I ask you what is the current value in branch 1 and branch 2, so then what you have to do, you have to apply KCL. So I1 plus I2 will be 9.3 milliampere, and these both the branches are similar, so I1 will be equal to I2. So 2 times I1 is 9.3 milliampere, and the value of I1 is 9.3 divided by 2. So this is how you can calculate current. Okay, so here you can see that I have applied KVL only in the one loop. and voltage between at this point, this is a single point, so it can have only one single value of voltage, and the value is 9.3 volt. Now case 2, both are 0. A is 0, B is 0. So it is now 0 means it is connected to ground, or you can apply 0 volt. Both are applicable. So this 0 volt is not sufficient to drive this diodes in on state. So off, D1 is off, D2 is off. V0 is not receiving any supply, so V0 will be also equal to 0 volt. Third case, A is 10, B is 0. So let's say this is A, point A, this is B. Okay, sorry. A is 10, B is 0. So this diode D1 will be in on state. This is 0, so D2 is off. So now you have to measure V0 again. So you can apply KVL into this loop. This is the complete loop. So again, the value will be same, 10 minus 0.7 minus V0. And V0 is 9.3 volt. And current I will be again 9.3 divided by 1 kilo ohm. So that is 9.3 milliampere. So in this case, now current in this branch, first branch, and in this vertical branch will be same because D2 is off. So the current will be equal. Only one branch exists. Whereas in this case, this I was bifurcated into two equal parts. Considering case 3, A is 0, B is 10. Okay, so this is A is 0, so D1 is off, B is 10. So it is a kind of a similar circuit, except that this is off, this is on. So again, the values will be same. I will be equal to I, this I1, this is I2, I2 will be equal to I. In this case, you can take it as I1. And V0 is 9.3 volt. Okay, so now you can draw a table for all the combination of input, value of A and B. Okay, so for 10, 10, I am writing 1. Now I am writing in terms of binary inputs, logic 1 or logic 0. So 1, 1, 0, 0, 1, 0, 0, 1. So for 1, 1, V0 was equal to 9.3. So 9.3 I can also take this as 1. So V0 is 1. Both are 0. This is the case. So V0 is 0. When 1, 0, when one input is at higher voltage, second is at lower voltage. This is the case. So output is again high. And the last case 0, 1. So again the output is high. So this is the behavior of logical OR gate. Okay. Only for 0, 0 the output is 0. For rest of the combination, output is always 1. If both the input is 1, output is 1. And if any one of the input is also 1, the output is 1. So this is how you design logic gates. This is the symbol of OR gate. Okay. Point A, input B, and this is output. And this is the behavior of logical OR gate. Okay. So what is inside the symbol? So this is one of the circuit. This is one of the possibilities. You can simply take 2 diode, 1 resistance. You can take 2 diode like this. Connect both the diode with a resistance and ground it. And this is equivalent to a OR gate. Okay. So digital circuit itself is created by this basic devices like diode, BJT, CMOS. ओके है हमारा बेसिक बिल्डिंग ब्लॉक वही है, डायोड है या बीजेटी होगा या सीमॉस होगा, बस उसको हम डिफरेंट तरीके से ऑपरेट करके डिफरेंट एप्लीकेशन डिराइव कर सकते हैं. सो many more gates can also be derived by changing the combination like AND gate, NOT gate. Okay, so you can try, आप ट्राई कर सकते हैं इस गेट्स के डिफरेंट कॉम्बिनेशन को. वैसे तो बॉयलस्टैड में सब दिया हुआ है, बट आप एक बार कोशिश करना खुद से डिराइव करने का. जैसे फॉर एग्जांपल AND gate. So for input A and B, you can have 4 combinations 0 0 0 1 1 0 1 1, and output will be 1 for this combination when both inputs are 1, otherwise it is 0. Okay, so you again need to input A and B. Okay, so 2 diodes will be required, and 1 or 2 resistance will be required. So try to derive this and get architecture in this manner. करके देखना, फिर हम डिस्कस करेंगे नेक्स्ट क्लास में उसको. So these kind of questions can be asked to you. This kind of question can be asked to you in exam or in any competitive exam or quizzes. If you are appearing for quiz, so some short question like this kind of questions can be given to you. So please practice it. Okay, very basic concepts are involved, so don't get confused. More and more practice, less and less confusion. So now moving to our next topic, that is half wave rectifier. Now we will be starting the topic rectifier. Okay, so rectifier, in this we will study first half wave rectifier, and the second we will study full wave rectifier. Okay, so what is rectifier? What is the basic purpose of rectifier? So it is a part of AC to DC conversion circuit. AC to DC conversion circuit. Okay, because you are receiving sine wave. In our household supply, we are receiving a sine wave of magnitude 230 volt, around 230 volt, and frequency 50 hertz. But what if we want to operate our laptop, mobile, and other devices which operates on DC battery? किसी भी डिवाइस में DC बैटरी लगा हुआ है, मतलब वो DC पे चलता है. Okay, so now you have to use this voltage source and you have to operate this. Okay, so जो आपका चार्जर होता है, लैपटॉप चार्जर, मोबाइल चार्जर, in that charger you have AC to DC converter. Okay, so what this is incorporated in your charger, AC to DC converter, and also it will step because your mobile is laptop is operating on 20 volt, mobile is around 4 volt, so step down process also need to be done. So 230 to 20 volt, and like this, a straight line. The frequency of this signal is 50 hertz, and the frequency of DC signal is 0 hertz, no variation, simply a straight line. So frequency of this DC signal is 0 hertz, and frequency of your household supply is 50 hertz, but you can have any frequency. In lab we have function generator, so we can have frequency in megahertz range also, 10⁶ hertz also. Okay, so this is the main purpose of rectifier. So it is one of the part of AC to DC conversion circuit. This is having many blocks. So one of the block is this rectifier circuit. So we have two kind of rectifier: half wave, full wave rectifier. In full wave, we have to study again two types of rectifier. First is center tap full wave rectifier, and second is bridge rectifier. So we will see all this circuit one by one. Okay, so what is your half wave rectifier? Starting with half wave rectifier. So if you provide a sinusoidal wave, any sinusoidal wave or a triangular wave, square wave, any kind of wave like this, you have provided a square wave or triangular wave, something like this, to your half wave rectifier circuit. So half wave rectifier, I am using short form HWR. So the output will be, for sine wave you will have a wave something like this. For square wave, something like this. And for triangular wave, something like this. So you will only receive the positive part. Okay, let's say this is the axis. This is the axis. This is positive, negative, positive, negative. This is the axis. This is voltage. This is time. So you will only receive the positive half. So this circuit, half wave rectifier, only allows the positive part of the input cycle to pass through it, and it will block the negative part. Okay, so if this is 0, this is t, the time period of this wave is t, and this point will be t by 2. So you will receive wave from 0 to t by 2, and from t by 2 to t, no wave will be present. Then t to 3t by 2, then 3t by 2 to 2t. No output is there. So this is the behavior of half wave rectifier circuit. Okay, 0 to t by 2, like this. This is same for all. Okay, time period of this wave is input wave. Let's say it is capital T. So time period, this is also periodic. This is one period, then again repeating, then again repeating. So time period of this output wave is also T. Time period is again equal to T. Okay, so now how to design this circuit? So it is very simple. You just need one diode and one resistance. That's it. That is all required to design a half wave rectifier. So this is your AC voltage source. Plus relative plus is here, minus is here. You need to have one diode. That's it. Connect it to a resistance. Connect this. You can connect the negative part to ground and measure voltage across this resistance. Okay, you can connect two probes here to measure the voltage. So V0 will be equal to VR. Okay, this is the simple schematic of half wave rectifier. Now how it is functioning? What is the time? 13:40. We have 10 minutes. Okay. Okay, so if the diode is ideal, for ideal diode, considering that diode is ideal, so this is your input. Some for half cycle it will be positive. For next half it will be negative, positive, negative, positive, negative, like this. Vn and T, and this is your circuit, and we are considering ideal diode. Okay, so first, for positive half cycle of input, for positive half cycle of input, this diode D will be in on state, D will be in on state, and you can replace this diode with a short circuit. Okay, so now this will be your equivalent circuit. A simple wire, a resistance R plus minus, and this is resistance R. Okay, so by simple applying KVL, you can say that V0 will be equal to Vin. Exactly, V0 is exactly equal to Vin. All the voltage, all this voltage variation will be field across this resistance R. Okay, so let's say this is V0. Parallel to Vin, I am drawing the output waveform V0. So this is positive half, so V0 is exactly equal to Vin. This is the case. So 0 to T by 2. Second, for negative half cycle of input, D2 will be off. You have to replace D2 with an open circuit. So this will be the case. This will be the equivalent circuit. no current will flow. Okay, in this some current will flow that can be again calculated by Ohm's law. So in this in the second case, no current will flow, hence VR is equal to 0. So you have 0 voltage for t/2 to time t. So this will be your output waveform. Suppose this is maximum value Vm. This is maximum value at this point Vm. So this will be also equal to Vm. Okay. Again, positive cycle will appear. Again, output will follow input, then 0. Like this. So very simple operation is there. Okay. And again, you are following the same thing. When diode is on, replace it with its equivalent circuit. When diode is off, open circuit it. That's it. The two things you have to apply again and again for all the applications. Okay. So this is the operation of half wave rectifier for ideal diode. Now what will happen if we replace the ideal diode with real diode? Okay. So this case will be remains as it is. Case 2 will be remain as it is for negative half cycle of input. D2 will be off and VR will be 0. The only difference will be in first case. So now for silicon diode, or I can say for real diode, with knee voltage Vk. Knee voltage Vk. So first case for positive half cycle of input, for positive half cycle of input. Okay, now you have two sub cases. Case A, when Vin is less than equal to Vk. Okay, because now your input is rising something like this. It is not instant like a square wave. It is a sine wave, so it is rising like this from 0 to some value, reaching up to Vm, then again falling back to 0. So 0 to Vk, let's say this point is Vk. Between 0 to Vk, Vin will, this condition will exist, Vin is less than Vk, so diode will be off. Okay, because this is the minimum voltage to turn it on. So diode will be in off state, and this will be the equivalent circuit. Again, off state means you have to open circuit it. So V0 is equal to 0. Okay, no current will flow. Open circuit, broken circuit, so V0 is equal to 0. Case B, when Vin is greater than Vk, your diode will be in on state. Okay, so diode is on. So replace your diode with a voltage source Vk, like this. Then resistance plus minus, this is ground, this is external resistance R plus minus Vk. So now what will be the value of voltage? V0, VR or V0? You can, VR and V0 are same thing. So what will be the value of V0? Apply KVL into this loop. So by KVL, this is Vn, this is Vn minus Vk minus V0 is equal to 0. So V0 is equal to Vn minus Vk. So this is constant, this Vk value is constant. Okay, so V0 will be always less than Vin by this amount, Vk. Okay, so now how to plot this? Suppose this is your Vin. Okay, I should magnify the positive half. So this is positive half, 0 to t/2. This is your Vn. This is your t. So V out. Okay, so what you can do? The boundary condition was Vk, so you can take a point approximately around this. Okay, let's say that this point is Vk volt. This is also Vk volt, and now you have to draw the output voltage. So whenever your Vin is less than Vk, diode will be off. So you can drop a vertical line from this point to this t-axis of V0. Okay, so the two vertical line. So this one, V0 will be 0 when Vin is less than Vk, and when Vin is crossing this Vk, so yeah, this V0 will be given by Vin minus Vk. So same sine wave, because Vin is a sine wave subtracted by a DC value. So sine wave magnitude Vm minus this Vin minus Vk. So it will be a sine wave. Okay, but this time, let's say this is the peak value. So this will be Vm minus Vk. Okay, if I superimpose this, I can also superimpose both this waveform onto a single axis. So this is V. So let's draw this output input waveform green in color. So this is your input waveform, and this yellow in this blue in color is representing your output waveform. So this up to Vk, it is 0. Then it is following your input waveform. Then again it is 0. So let's say this is the point. So it is again 0. So this difference is of Vk. Okay, and this is Vin minus Vk. So this is the difference. When you are using ideal diode, V0 will be exactly equal to Vin. When you are using real diode, V0 will be equal to Vin minus Vk. The difference of Vk is there. Okay, and for the negative half, output is 0, like this. So we will derive some parameters for this half wave rectifier. Yes, tomorrow we have a class at 1 p.m. I think 11:20. So tomorrow we will discuss some parameters like average DC voltage, efficiency. Okay, and then we will start full wave rectifier. So have a nice day. And if you have any doubt, you can ask tomorrow.